Let's continue our discussion on semi-classical approach. Let us assume that a given atom initially raised to its excited level 2 of energy 2 is decaying by spontaneous emission to level 1 of energy E1. We will assume that the two levels are non-degenerate. So let's discuss here. That is psi 1 at r comma t is equals to u1 r as position exponent here a negative j into E1 energy E1 over h bar times t as the wave function psi for a given atom that decays from energy 1 from excited level 1 at energy 1 and for level 2 here psi 2 r comma t which is equals to u2 that's energy density u2 r exponent here negative j into E2 energy 2 over h bar times t for level 2 b the corresponding wave functions where u1 u2 are the eigenfunctions of the two stationary states. R denotes the coordinate of the electron undergoing the transition. The origin being taken at the nucleus, and h bar is equal to h over 2 pi. H is the h bar is equal to h over 2 pi, and the value of h is equal to 6.602 times 10 to the power of negative 34. When the atom is undergoing from the level 2 decays to the level 1 transition due to spontaneous emission, its wave function can be expressed as a linear combination of the wave functions of the two states. That is psi, the sum of psi is equal to the sum of psi on or wave function 1 and wave function 2. That is A1 at t psi 1 plus A2 at t psi 2, where A1 and A2 are time-dependent complex numbers. Note that according to quantum mechanics, we have here magnitude of A1 square plus magnitude of A2 square, which is equals to 1. That's the magnitude of A1 square and A2 square is equal to 1 according to the quantum mechanics. And thus A1 square and A2 square represent the probabilities that at time t the atom is found in state 1 or 2 respectively. That is the value of A1 square and A2 square represents the probabilities of the atom found in state 1 or 2 respectively. To understand how spontaneous emission arises, let us calculate the electric dipole moment of the atom, mu. Then, according to quantum mechanics, we have the electric dipole moment of the atom, mu, which is given by negative integral E, that is the charge of the atom, times the absolute value of psi square r dv. Here dv is the elemental volume of the charge occurs. That is, v is the volume of the charge occurrence. Then where E is the magnitude of the electric charge, that is, E is the magnitude of the electric charge, and the integral is taken over the whole volume of the atom. The form of this equation can be readily understood by noting that E psi square dVr is the elemental charge expected in the volume dV at position r, and that this charge reduces to elemental dipole moment, that is d mu, which is equal to the negative E absolute value psi square dV and r. This is enough for today. We will proceed for the next class.